Okay, so this is going to be a wrap-up of the first part of the lab, which is on work, in case you need it for if you were absent or if you just need some more guidance on it, all right? So as a reminder, what we did was we had 3 pulley systems, and we called them 1, 3, 5 because of how many strings were wrapped, okay? Like this one was just wrapped once, this one was wrapped, like somehow it made 3 bars or something, and then this one made 5, all right? And when you pulled down block 1, you had to pull with a lot of force, but you didn't have to pull with much distance to raise it up. Block 5, on the other hand, didn't take a lot of force, but the distance was very high. You had to pull this really far, okay, to get the blocks all to raise to the same height, okay? So when each block started with no energy, each block ended with the same amount of EG because all the blocks were the same mass and they were all raised to the same height. Okay, and this is all stuff that's going to need to be written somewhere in your lab. Okay, same height. Okay, so they all were given the same EG. All right, so what happens when we graph these, 1, 3, and 5, okay, you should have the numbers from the lab, right? But basically the first one kind of looked like, I think it was a force of 8 and only 0.02. This is force and distance, okay? This one had a force of 2, all right, for about, I don't know, half, almost a meter, 0.8 I think it was, 2 and 0.8. Okay, and this one had a really tiny force of 0.8, but it did it for super long 2 meters, all right? So what you'll see when you calculate all these areas, okay, it's just a box, so it's going to be base times height. You're going to get something like 8 newtons times 0.2 meters, and each area came out to be 1.6 joules. Or if it's Miss Madrano's class, yours were slightly different, but somewhat close, okay? All right, so all of these areas, when you look at them, even though they're different shapes, right, like this one's kind of tall and skinny, this one's kind of short and wide, and this one's sort of middle, they all came out to have the same areas. Okay, so that might be something that you know in your evidence, that all the areas of the force versus distance graphs were the same. Okay, all right, they all came out to be the same area. Okay, and if we look at the units of this, we know a Newton meter is a joule, so we know that this is going to be somehow related to energy. All right, and in this specific case, the way that we're going to explain it is we see that we had no energy to start. We have the same amount of energy put in. Well, where did that energy come from? Okay, it can't just come from nowhere, right? Because of the law of conservation of energy, it has to come from somewhere, meaning I did what we call work. I did work on it, okay? Right, and which pulley had the most work done? Well, if you look at the areas, even though they look different, we can see that all the areas are equal. That means they all did the same amount of work. Okay, in my classes, they all did 1.6 joules, okay, depending on what data you got in other classes. It should have been roughly close. If it wasn't close, you should just say that it should have been close, okay, because the measuring devices we have are not the greatest. That's why I sort of adjusted my data so that it was cleaner, okay? All right, let's see, what else might you need to say in the CERs, okay? So the claim, we said what was the formula for work, okay? So when we look at this graph, we know that this area is the same, and also they got the same EG. So we can conclude that the work is the same on all of them. So when I take this area, base times height, okay, the base of the triangle is the distance, the height is the force, okay, and I know that that's the work done. Okay, and usually we write force times distance. You can write it either way, it doesn't matter. Okay, so this is the equation for work. So anytime you apply a force over a distance, you're going to do work on the object and then therefore give energy to the object. Okay, because it has to come from somewhere. It can't just appear. You have to do something to make that happen. That energy is coming from you, if you keep looking back. Okay? All right, so when you write the CER, do your best. We think maybe in retrospect we didn't quite ask the right question. Okay? If you haven't written it yet and you want to change it, the key question to say what are the factors that affect work. After working with some kids after school, we think that might have been a cleaner question. You could change it to that if it makes more sense to you. If not, you can just keep it as the equation. It's kind of asking the same thing anyway, because the equation does say what the factors are. But and then the evidence should be only things you see. Don't explain. Don't explain, oh, I see the area, that means it's the work. No, that's reasoning, okay? You just, I see that there were boxes, so this would be for evidence. I see that the masses are the same. I see that they were raised to the same height. When I made a graph, I see that the pulley 1 took a lot of force in a little distance, pulley 5 took a little force in a lot of distance, okay? I can see that the areas are all the same, all right? So these are things that should go in your evidence, okay? Your reasoning, you're going to go through and you're going to answer those questions that were given, okay? And in paragraph form, don't just write a list of questions. I don't want that. I want it to be a nice, clean paragraph. This is the most important part to me, is that you can sort of explain all of this, okay? All right, and then if you have any other questions or you need help, I'll be around Monday after school. Someone should be around Tuesday after school, and then probably I'm out, and then Miss Medrano will be there to help you guys, and Mr. Murphy can help you also, okay? That is all.